Have you ever really stopped to think about time? I mean, not just, the clock on the wall, but this constant push forward. It seems so absolute, so unchangeable. We all kind of dream about time travel, right? It's classic sci-fi, that idea of jumping back or seeing the future. But then you dive into quantum physics, and suddenly the rules just go out the window. Things are weird down there. Particles in two places at once, affecting each other instantly across space. It sounds impossible, but it's real science. It makes you question everything. So here's the big question this research tackles. What if you could mess with time? Not for us, not for people, but for the smallest bits of matter. Well, hold on to your hats because some scientists in Austria, they've actually done something incredible. They're talking about sort of quantum time travel for particles. It's becoming real. Welcome to the Deep Dive. We're here to break down the research that's changing the game. Today, we're digging into how scientists can literally rewind and fast forward the state, the age of quantum particles.
Yeah.
Sounds like a movie plot, I know, but it's happening now.
And hey, if you like these kinds of explorations, do give us a like. Maybe subscribe, helps us keep bringing you this stuff. Let us know in the comments what else you want us to dive into. Okay, so let's get into this. First things first, we absolutely need to be clear. This isn't your H.G. Wells time machine, all right? We're not talking about sending people anywhere. This is all happening at the quantum level. Tiny particles, their rules are just different. It's about controlling how they evolve through time, their state. And the key piece of tech here is this really clever device called the quantum switch.
Yeah.
Think of it like a super precise remote control, or maybe like a traffic controller for light beams. The researchers had a great way of putting it. They said, classical physics is like watching a movie in a cinema, start to finish, that's it. But quantum systems, they're more like watching at home. You can rewind, fast forward, skip around. That analogy really clicked for me.
It really does capture it well. And the level of control they've achieved is, well, it's remarkable. The team, Miguel Navasco's at the Austrian Academy of Sciences and Philip Walther's group at the University of Vienna, they've developed something quite special. They call it a rewind protocol. And they demonstrated it using photons, particles of light, and a really intricate setup with crystals and this quantum switch you mentioned.
Okay, so how does that rewind actually work?
Well, this is the truly mind-bending part. They could send a photon through their system, let it change, let it evolve, and then, using the switch, they could snap it back to its exact original state.
Its original state?
Exactly, as if its journey never happened. And here's the kicker, the bit that's really hard to grasp. They did this without needing to know what actually happened to the photon along the way.
Wait, without knowing anything about its path or interactions?
Precisely. Imagine rewinding a tape you haven't watched. And it just resets perfectly. That's basically what they achieved with the quantum particle. It fundamentally challenges our ideas of history and information.
That just feels impossible based on everyday experience. How can you undo something if you don't know what the something was? But what was the big mental hurdle there?
Well, the hurdle is our classical thinking, right? We think event happens, leaves a mark. To undo it, you need all the details. But quantum mechanics is different. Particles can exist in superpositions, like exploring multiple paths at once. So the leap was realizing maybe you don't need to track one path. If it explores many possibilities, you can interfere with those possibilities to guide it back. You're manipulating the potential histories, in a sense, exploiting the quantum weirdness itself rather than fighting against it.
And it sounds like it was incredibly difficult to build. I saw that quote from Philip Walther saying it was one of the most difficult experiments we've ever built for a single photon.
Oh, absolutely. The engineering required is immense. Controlling single photons with that precision is right at the cutting edge. It highlights how significant this is. It's not just theory.
Right. But, okay, so they figured out rewind. But the story doesn't stop there, does it? They went even further.
That's right. They didn't just hit rewind. They also figured out how to effectively fast forward time for these particles, too.
So they have the whole remote control now. How does that work? You can't just create time, can you?
Well, no, not exactly. Navascu's explained it really well. He said, basically, to make a system age 10 years in 1 year, you must get the other 9 years from somewhere.
Ah, okay. So it's not generating time. It's moving it around.
Exactly. It's redistribution.
Yeah.
In one experiment, they took 10 identical quantum systems. They managed to effectively steal a year's worth of evolution or aging from 9 of them. And they transferred all that stolen aging 9 years worth onto the 10th system. So that one system experienced 10 years of evolution in just one actual year.
So it's like concentrating the aging process. Does that suggest some kind of like a conservation of evolution almost, that you can move it between systems?
That's a really interesting way to think about it. It's not quite a fundamental law like energy conservation, but in this controlled quantum context, yes, the evolutionary progress can be shifted around. It really underlines how interconnected these quantum systems can be and just how fundamentally bizarre quantum mechanics is compared to our world. This level of control over a system's evolution, speding it up or slowing it down like this, it's completely new.
It really makes you think, what else could you do with that kind of control? But let's address the elephant in the room. The big question everyone's probably asking, does this mean human time travel? And okay, let's be really clear on this. No, absolutely not. Your body, my body, we contain an astronomical amount of information. Every atom, every connection, the researchers themselves crunch the numbers. They estimate it would take millions of years just to rewind 1 single second of a person's life using these methods. So fascinating for particles.
Yes.
Personal time machines.
Yeah.
Still firmly sci-fi.
Precisely. The real goal here is much more practical, though still pretty revolutionary. It's about quantum computers. Quantum computers store information in these super delicate things called qubits. They can be 0, 1, or both at once. That superposition gets them incredible power. But that delicateness is also a problem. Qubits are incredibly sensitive to noise, to errors. A tiny disturbance can mess up the whole calculation.
Right, the error problem is a huge challenge for quantum computing.
Exactly. And that's where this rewind protocol could be a game changer. If an error happens during a quantum computation, imagine you could just hit rewind, go back to the state before the error occurred, fix it, and continue. No need to start the whole complex calculation over.
Wow, okay, that would be huge, like an undo button for quantum errors.
That's a great way to put it. Philip Walther actually said, "We are convinced that it has technological applications. A rewind protocol can be used to reverse unwanted errors or developments. It could make quantum computers much more robust and efficient."
And presumably, this isn't just tied to photons, right? They could adapt this for other types of qubits.
That's the hope, yes. The principles should apply to other quantum systems. So you could see this technology potentially being built into different kinds of quantum processors, maybe even more complex ones down the line. It could really change how we manage quantum information.
Okay, so stepping back a bit, why is this such a big deal compared to, classical physics? We have this idea, the arrow of time, right? Arthur Eddington talked about it. It's tied to the second law of thermodynamics. Things get messier, entropy increases, time only goes forward. You can't unscramble an egg.
Spot on. In the classical world, that arrow is pretty rigid. Sure, there's some theoretical tricks like phase conjugation, but real-world noise and complexity always get in the way of a perfect reversal. The big question for quantum systems has always been, can you truly reverse the evolution without knowing everything about its past? Because needing to know everything makes reversal practically impossible.
And previous attempts had limitations.
Right. Some methods only work probabilistically, sometimes.
Mm-hmm.
Others needed very specific knowledge of the state or the interactions, or they were just too slow. This new protocol is different. First, it works for any two-level quantum system, any qubit. Second, their experiments showed incredibly high success rates, over 95% accuracy.
95%. That's really high for quantum stuff.
Hmm.
What's the missing 5%? Is it fundamental or just experimental fuzziness?
It's mostly those unavoidable experimental imperfections. Maintaining perfect quantum coherence is incredibly hard. There's always a little bit of noise leaking in from the environment, so it's technical limitations they're constantly working to minimize. But getting over 95% fidelity shows how robust the core protocol actually is, even in a real lab.
Okay, that makes sense. And the other key thing.
It runs in real time. If you want to rewind the system's evolution by 5 minutes, the process takes 5 minutes. That practicality is crucial for potential applications.
So how do they do it? What's the quantum magic behind the curtain? You mentioned something about non-commuting operators.
Yes, that's at the heart of it. It sounds technical, but the basic idea, like your socks and shoes analogy earlier, is perfect. In quantum mechanics, the order you do things fundamentally changes the outcome. AB is not the same as BA.
Okay, order matters. How does that let you rewind time?
Because order matters, you can make the system evolve through a superposition of different time paths or different sequences of operations simultaneously. It's like it explores multiple timelines at once.
Multiple timelines.
Yeah. And by cleverly controlling how these different timelines interfere with each other, using things like wave plates to create different evolutionary paths, different Hamiltonians technically, and then using fast optical switches and that quantum switch to mix them, they can guide the particle back. They essentially cancel out the forward evolution and reinforce the path back to a previous state, regardless of which specific path it seemed to take. They even build some active error correction into the process itself.
So it's not just theory. They built machine, run the experiment, and got the results with high accuracy.
Exactly. This is experimentally verified physics, opening doors not just for better quantum computers, but also giving us these really deep insights into how time itself behaves at that fundamental level. It's much more flexible than we thought.
What an incredible journey. We've gone from this almost unbelievable idea of manipulating time for particles, all the way to potentially game-changing applications for the future of computing. It's really something.
It absolutely is. And I think the key takeaway is that while, jumping in a DeLorean is still fiction, this work shows physics can bend the clock back, at least for these tiny systems. It tells us the rules of time we experience are maybe not the only rules. Down at the quantum scale, things are fundamentally different, much more dynamic.
So you have to wonder then, right? If time can be manipulated like this, like a remote control for particles, what other fundamental rules might be more pliable than we currently think? How could this change technology in ways we can't even imagine yet? It really drives home how these deep, fundamental breakthroughs, the ones that seem purely abstract, often end up being the foundation for the biggest leaps forward later on. Definitely something to keep pondering. Well, thank you for joining us on this deep dive into the weird world of quantum time. We hope you found it as fascinating as we did. We'll catch you next time for another exploration at the frontiers of science.